Introduction. The universe is full of ideas that push the limits of what we understand. Theories so unsettling that even scientists feel a quiet tension when they face them. Tonight's journey takes us into the concepts that challenge our sense of reality, our future, and our place in the cosmos. If you're ready to explore the mysteries that keep brilliant minds awake at night, settle in. Let's begin. The simulation hypothesis. The simulation hypothesis proposes that the world is not an independent physical reality, but a constructed environment generated by an advanced computational system. Within this framework, every object, particle, and phenomenon is the result of encoded rules operating with consistent precision. The theory suggests that the stability of natural laws, the structure of matter, and the mathematical harmony of the universe are not random occurrences but the product of an underlying informational architecture. This concept draws its strength from the remarkable predictability of physics and the digital-like behavior observed at the smallest scales, where matter can resemble packets of discrete information rather than continuous forms. In this narrative, the universe behaves like an immense program running on a substrate far more sophisticated than anything humanity has developed. The fundamental constants, values that never change and control the formation of galaxies, stars, and all known structures, serve as evidence of a system calibrated with extraordinary accuracy. Even small deviations in these values would prevent the emergence of life or stable matter, which gives the impression of deliberate configuration. The uniformity of cosmic microwave background radiation, the quantization of energy levels, and the computational nature of quantum interactions contribute to the sense that reality follows encoded instructions rather than unfolding randomly. Observers within this system perceive the world as solid and continuous. However, at microscopic levels, the components of reality behave according to probabilistic rules. This behavior can resemble optimization processes, where only the necessary information is rendered when observed. Some interpretations of quantum behavior highlight this effect, describing a mechanism in which events take definite form only during measurement, similar to how a simulation allocates processing power only when needed. In this view, the universe conserves informational resources, generating detail selectively rather than constantly computing every region at maximum resolution. The idea is not presented as a dismissal of physical phenomena, but as a different interpretation of their origin. It assumes that the laws of physics are the operational guidelines of the system, functioning consistently to maintain coherence. The continuity of time, the emergence of complexity, and the evolution of biological life would be emergent properties built atop these foundational mechanisms. The vastness of space, with its expanding frontiers, could represent a dynamically generated environment, extending as the system processes new regions. In this structure, entities experience time and space as fundamental components, even though they might only be features of the informational framework. Supporters of the hypothesis argue that technological trends in human history demonstrate how simulated environments become more sophisticated with each generation. Although current technologies remain primitive compared to the scale of the proposed system, they indicate a direction of development in which fully immersive, consistent simulations might eventually emerge. These analogies do not serve as direct evidence but as conceptual models, showing that simulated realities are compatible with technological evolution. The hypothesis extends this possibility into the far future, imagining civilizations with computational abilities capable of building universes with stable physical laws and self-developing inhabitants. Within such a scenario, consciousness becomes a product of the system, arising from the interactions between informational structures. The experience of selfhood, memory, logic, and perception forms through patterns encoded within the simulated framework. From this standpoint, consciousness is not an exception but a function of complexity. As systems grow more intricate, they develop awareness as a natural consequence of emergent processes. Whether these processes originate in biological structures or computational environments becomes secondary, as the underlying mechanism still produces subjective experience. The simulation hypothesis treats reality as a coherent, internally complete structure. It does not suggest external interference or direct manipulation but focuses on the existence of a deeper layer beneath observable physics. The inhabitants of the system operate according to the rules encoded within it, forming societies, discovering scientific principles, and exploring the environment. The consistency of these experiences reinforces the impression of an independent universe, even though it might be underpinned by processes outside the perceptual limits of its participants. The concept introduces the possibility that the universe has a finite level of complexity, governed by limits similar to those in computational systems. These limits might explain phenomena such as maximum physical speeds, quantized energy states, or the finite amount of information that can be stored in a region of space. The structure of black holes, the distribution of matter, and the relationship between entropy and information all align with principles that resemble computational constraints. While these parallels do not prove the hypothesis, they contribute to the sense that the universe may function according to informational rules. In this framework, the emergence and evolution of civilizations are natural outcomes of the system's design. The progression of species, the development of technology, and the formation of cultures occur within the boundaries of encoded parameters. As civilizations advance, they may attempt to understand the foundation of their reality, exploring physics, mathematics, and cosmology. Their discoveries reflect the structure of the underlying system but do not necessarily reveal its origin. The simulated environment remains complete and self-contained, providing all necessary components for the existence and growth of its inhabitants. The simulation hypothesis does not aim to reduce the importance of lived experience. Instead, it offers a different interpretation of what existence might be. It describes a universe built upon an informational base that operates with precision and consistency, generating the environment in which life unfolds. Whether the system was created intentionally or arose from natural computational processes is beyond the scope of the hypothesis. Its primary focus lies in the nature of reality and the possibility that physical phenomena are expressions of deeper informational structures. According to this view, the universe remains vast, coherent, and meaningful, even if its foundation rests upon encoded rules. The Great Filter. The Great Filter is a concept that attempts to explain the striking silence observed in the universe. Despite the vast number of stars, planets, and potentially habitable environments, humanity has never encountered signs of advanced civilizations. The theory proposes the existence of a barrier, an immense threshold that prevents most forms of life from progressing to a stage where they can expand beyond their home world. This barrier can exist in the distant past, in the present, or somewhere ahead, shaping the destiny of every emerging species. The idea begins with the recognition that the conditions necessary for life appear far more widespread than once imagined. Planets with stable climates, sources of water, and environments suitable for chemical evolution exist in many regions of the cosmos. Yet the universe remains quiet, lacking the signals, structures, or traces that would be expected if civilizations frequently reached high levels of development. This absence is the foundation of the theory. If the universe contains many opportunities for life, then something must be limiting its progression. One interpretation places the barrier at the earliest stages of biological formation. In this view, the leap from simple molecules to self-replicating structures is exceedingly rare. The emergence of cellular life, with its organized systems and complex interactions, might represent a step so improbable that it occurs only a handful of times across cosmic history. If this is the location of the barrier, then humanity has already surpassed it. The existence of intelligent observers would mean that one of the most difficult steps has been completed, and the path forward might be less constrained. Another possibility positions the barrier later in the development of life. The evolution of multicellular organisms, the rise of complex ecosystems, and the emergence of tool-using species may require conditions that seldom come together. Civilizations capable of forming abstract thought, constructing societies, and developing technology could be exceedingly uncommon. In this scenario, the appearance of a species able to contemplate the universe is an extraordinary event. If this is the case, then humanity stands among the few that have reached this stage, having overcome the major obstacles of biological and social evolution. A third interpretation shifts the barrier into the future. This perspective holds that civilizations capable of technological advancement often encounter challenges they cannot withstand. As species gain mastery over energy, matter, and large-scale systems, they also create forces that can destabilize their own existence. These challenges can emerge from environmental transformation, resource depletion, or self-generated systems that escalate beyond control. The barrier, in this case, would be a pattern in which advanced civilizations rarely survive long enough to expand into space, leaving the universe silent even when intelligent life arises. This future barrier is often described as the most unsettling interpretation. It implies that civilizations tend to reach a certain point of development and then encounter conditions that are difficult to overcome. These conditions may be the result of internal dynamics, natural cosmic processes, or technological thresholds that require exceptional stability to manage. If the great filter lies ahead, humanity is approaching a stage where its resilience will be tested on scales greater than any in its history. The theory does not attribute intention or external influence to this barrier. It treats the process as a natural consequence of the universe's structure, driven by probabilities and environmental constraints. Every step in the emergence of a civilization requires a chain of rare events, each dependent on the previous one. The more complex a species becomes, the more vulnerable it may be to disruptions that can alter or halt its development. Over long cosmic periods, these disruptions accumulate, shaping the distribution of advanced societies. Supporters of the concept examine the known transitions in Earth's history. The formation of stable elements, the appearance of oceans, the development of early cells, and the rise of increasingly complex organisms all represent pivotal stages. Each stage depended on delicate balances, narrow windows of opportunity, and environmental conditions that could easily have shifted in another direction. These ancient events illustrate how fragile the path to advanced life can be. The theory extends this fragility across the universe, suggesting that similar challenges shape countless worlds. The Great Filter also influences the way civilizations perceive their place in the cosmos. If the barrier lies behind humanity, then its existence is a statistical triumph. It would represent a past filled with improbable victories, each one enabling the next stage of development. In this view, humanity stands as evidence of rare success in a universe where the emergence of technological life is exceptional. If the barrier lies ahead, then it becomes a reminder of the challenges that accompany advancement. Vacuum decay. Vacuum decay describes a scenario in which the fabric of the universe is not in its most stable form. According to this concept, the space that surrounds all matter and energy may exist in a state known as a false vacuum. It behaves as stable under normal conditions, yet deep within its structure lies the potential for a transition to a more fundamental state. This transition would not resemble a gradual shift but an abrupt transformation, spreading across space with absolute finality. The theory arises from quantum field models, where each field has levels of stability that define the behavior of fundamental particles. In this framework, the universe may occupy a high-energy configuration that persists due to the immense scale of cosmic processes. Although it has remained stable for billions of years, the structure of the false vacuum includes the possibility of collapse into a true vacuum, a lower energy state with different physical properties. This transformation would begin at a single point, where fluctuations allow the system to cross the boundary separating both states. Once this boundary is crossed, a bubble of true vacuum would form, expanding outward at extraordinary speed, reshaping everything in its path. The transformation would not be destructive in a conventional sense. Instead, it would redefine the underlying rules that govern the universe. The constants that shape matter, energy, and forces would shift to new values consistent with the true vacuum. The structure of atoms, the behavior of particles, and the interactions between fields would be altered. Objects, stars, and even the fundamental components of space would no longer behave as they do in the current configuration. The transition would be absolute and final, leaving no region unchanged. The idea does not arise from hypothetical speculation alone. Quantum field theory provides numerous examples of metastable states, where a system appears stable despite existing above its lowest possible energy level. Water supercooled below its freezing point, or elements that maintain form under specific pressures, offer small-scale analogies. These systems remain intact until a disturbance triggers a transition. In the cosmic model, fluctuations within quantum fields can act as the triggering mechanism, allowing the formation of a region that shifts into a more stable structure. Once created, this region grows because the new state is energetically favored. The possibility of vacuum decay depends on the properties of fundamental particles and fields. Certain measurements suggest that the current balance between particle masses may place the universe near a boundary between stability and metastability. If the fields are perfectly stable, the false vacuum scenario becomes irrelevant. But if the fields occupy a metastable configuration, the transition remains a distant yet conceivable outcome. The theory highlights how delicate the balance of physical constants can be, with small changes potentially shifting the entire structure of reality. In large-scale cosmology, the universe appears calm and predictable. Galaxies form over immense periods, stars follow consistent cycles, and matter behaves according to reliable laws. Yet vacuum decay introduces a contrasting perspective, emphasizing the hidden potential for sudden reconfiguration. The process would not produce early warnings or detectable precursors. Because the bubble expands at extreme speed, any region would experience the transition immediately upon contact. The event would be silent, instantaneous, and total, leaving no detectable signs before it reaches any observer. Despite its dramatic implications, the theory remains a mathematical possibility rather than a forecast. The stability of the vacuum depends on the exact structure of the fields that define the universe. These values are measured with high precision, yet small uncertainties influence the interpretation. Some models place the universe comfortably within a stable region, while others situate it near the edge of metastability. The theory emphasizes that cosmic structures rest upon a fine balance of parameters, each contributing to the long-term behavior of the vacuum. Vacuum decay also serves as a reminder of how little is known about the earliest moments of cosmic history. The universe emerged from conditions of extreme density and temperature, where fields behaved differently from their current form. As the universe expanded and cooled, it transitioned through multiple phases, settling into the configuration observed today. Whether this configuration represents the absolute ground state or a temporary plateau remains an open question. The persistence of the false vacuum would depend on the dynamics set in motion during those early transitions. The theory provides insight into the relationship between energy, stability, and the nature of physical laws. It suggests that the properties perceived as permanent are dependent on the structure of the vacuum. Every aspect of matter, from the charge of particles to the forces that bind atoms, exists because the vacuum holds specific characteristics. If the vacuum shifts, the laws shift with it. This connection reinforces the idea that physical reality is deeply tied to the state of the underlying fields, and that stability on cosmic timescales requires these fields to remain constant. Vacuum decay is not presented as an imminent occurrence but as a theoretical boundary condition that defines the limits of stability. It reflects the understanding that deep beneath the visible structure of the universe lies a complex foundation shaped by quantum dynamics. The concept emphasizes the layered nature of reality, where familiar forms and forces arise from subtle balances that extend far beyond direct perception. Whether the universe occupies its most stable configuration or a temporary phase, the theory illustrates the intricate interplay between quantum fields and the large-scale behavior of cosmic space. Heat death of the universe. The heat death of the universe describes a distant stage of cosmic evolution in which all physical processes gradually slow, weaken, and eventually cease. This idea emerges from the study of thermodynamics, where energy naturally spreads from concentrated states into uniform distributions. Over vast timescales, the universe moves toward increasing entropy, dispersing heat and diminishing the ability of matter to perform work. In this distant future, the cosmos becomes a place of fading activity, where structures that once formed stars and galaxies drift into stillness. The process begins with the ongoing expansion of space. As galaxies move farther apart, the density of matter decreases, and the temperature across the universe gradually drops. Stars burn through their fuel, completing cycles that began billions of years earlier. Massive stars collapse into remnants, and smaller stars cool into dim objects that release their heat slowly into the surrounding space. This slow diffusion of energy is a key element of the transition, spreading warmth until it becomes too diluted to sustain further activity. In earlier stages of the universe, gravity shapes matter into galaxies, clusters, and complex structures. Over time, these structures lose their coherence as internal processes weaken. Stars reach the ends of their lifetimes, planets cool, and radiation becomes more evenly distributed. Black holes grow through the slow capture of surrounding material, concentrating mass into singular regions while the space between galaxies continues to stretch. The contrast between active regions and empty space diminishes with each passing era, forming a cosmos where energy is no longer capable of driving dynamic change. As countless ages unfold, even the remnants of stars begin to fade. White dwarfs release their stored heat, becoming cold, stable objects. Neutron stars and stellar fragments shift into deeper phases of cooling, radiating energy until they approach thermal equilibrium with the environment around them. The glow that once filled galaxies diminishes. The universe becomes darker, quieter, and increasingly uniform. At these scales, entropy continues to rise, driving the cosmos toward a final state where temperature differences barely exist. Black holes dominate the final stages of this long transformation. Over incomprehensibly large spans of time, they gradually release energy through a quantum process that emits radiation. This evaporation is slow but inevitable, reducing even the most massive structures into streams of particles that disperse across expanding space. When the last black hole completes this process, the universe enters an era in which no major structures remain. Only scattered particles and faint radiation continue to exist, drifting across a space that grows colder with each epoch. In this environment, the capacity to perform work, a requirement for all organized activity, approaches zero. Thermodynamic equilibrium takes hold when every region of space reaches nearly identical temperature and energy distribution. Without differences in energy states, processes such as motion, fusion, and chemical reactions cease. Matter loses the ability to reorganize itself, and the mechanisms that once built stars, planets, and life itself no longer function. The universe becomes a vast, dilute expanse where nothing new can emerge or transform. This final state does not involve abrupt changes. It unfolds gradually, shaped by the steady direction of thermodynamic laws. Energy continues to disperse, structures continue to weaken, and the cosmos approaches a limit where entropy reaches its maximum possible value. The heat death represents the endpoint of this progression, a state devoid of usable energy. At this stage, the universe remains present but experiences no evolution, no cycles, and no renewal. Time itself becomes a measure without meaningful events, marked only by the silent drift of particles through empty space. The concept highlights the close relationship between thermodynamics and cosmology. It illustrates how the large-scale behavior of the universe is connected to the fundamental behavior of energy, motion, and matter. Every process that occurs, whether the formation of a star, the orbit of a planet, or the decay of a particle, contributes to the gradual increase of entropy. Over immense durations, these contributions accumulate, guiding the universe toward equilibrium. The heat-death scenario also underscores the finite nature of cosmic complexity. Although the universe contains vast numbers of galaxies, stars, and dynamic systems, each one is subject to processes that lead toward uniformity. The diversity of structures visible today arose from the distribution of energy after the early expansion of the universe. As time progresses, contrast fades. Regions become indistinguishable from one another, and the capacity for new forms of organization diminishes. This distant future is shaped by known physical laws, projecting their consequences across scales far beyond ordinary experience. The process reflects the irreversible direction of entropy, which governs the transformation of energy in all contexts. Whether applied to small systems or the entire cosmos, the principle remains consistent. Over enough time, differences level out, energy spreads, and activity slows. The heat death of the universe represents the culmination of this trend. It envisions a cosmos that reaches absolute stillness, not through sudden transition but through gradual exhaustion of all usable energy. In this final state, the universe persists as a silent, uniform expanse, shaped by the long arc of thermodynamic evolution. Boltzmann Brains. The idea known as Boltzmann Brains emerges from the study of entropy and the behavior of systems over extremely long periods of time. It begins with the observation that the universe tends towards states of higher disorder. As energy spreads out and structures break down, the overall entropy increases. Within this framework, rare fluctuations can occasionally produce temporary pockets of order. These fluctuations do not follow gradual processes but arise spontaneously from statistical behavior. The concept proposes that, given enough time, these fluctuations can create complex formations, including self-aware observers. This perspective originates from models in statistical mechanics, where systems evolve through countless random configurations. Over immense durations, even highly ordered states become possible, although they are extraordinarily unlikely. The universe, when considered across spans far beyond ordinary cosmic timescales, can experience such fluctuations. The Boltzmann Brain scenario suggests that a conscious observer might arise directly from these rare events, formed briefly from the chaotic background of high-entropy space. In this theoretical environment, the brain does not develop through biological evolution or the formation of a species. Instead, it appears as an isolated structure emerging from a fluctuation. It would possess a coherent arrangement of particles capable of producing thoughts, memories, and perceptions. These memories would not reflect an actual history but would exist as part of the configuration that forms during the fluctuation. The appearance of such an entity would last only as long as the fluctuation remains stable. When the system returns to a state of higher entropy, the structure would dissolve. The scenario does not focus on the detailed functioning of consciousness but on the statistical nature of ordered states. A functioning observer, regardless of how briefly it exists, represents a pattern highly unlikely to appear in a disordered universe. However, when given infinite or near-infinite time, the probability of such an event becomes non-zero. The theory evaluates these probabilities within the context of a universe that continues evolving toward high entropy, where structured systems become increasingly rare yet still possible due to vast timescales. This concept introduces an unusual consequence. If the universe lasts long enough and entropy continues to rise, the emergence of isolated observers through fluctuations may become statistically more common than the evolution of entire civilizations. Complex structures such as galaxies, stars, and planets require low entropy beginnings and long-term stability. The evolution of life demands extended periods of order, intricate interactions, and favorable conditions. In contrast, a single fluctuation forming a temporary conscious structure requires far fewer coordinated steps. As a result, isolated observers could become increasingly likely in the distant future compared to civilizations arising through conventional processes. The idea also highlights the relationship between entropy and the formation of structure. In the early universe, energy was distributed in a way that allowed matter to condense into stars and galaxies. Over time, these systems evolve, disperse, and decay. As entropy rises, the creation of new large-scale structures becomes less likely. In contrast, small, short-lived structures formed through random fluctuations remain possible, although they are extremely improbable at any given moment. When the future of the universe is considered on astronomical timescales, these low-probability events accumulate into meaningful possibilities. From a cosmological perspective, the Boltzmann brain concept explores the boundaries of statistical reasoning. It examines how order can emerge from disorder without the need for long-term processes. The formation of a structured observer through fluctuation does not require a sequence of evolutionary steps or environmental support. It emerges fully formed, sustained only by the temporary conditions produced by the fluctuation. This scenario challenges traditional assumptions about how complexity arises, emphasizing that even highly organized systems can appear momentarily in an overwhelmingly disordered environment. The theory also has implications for models of cosmic longevity. If the universe expands indefinitely and continues approaching equilibrium, the opportunities for random fluctuations persist. The longer the universe exists, the more significant these fluctuations become in shaping its statistical landscape. As the frequency of conventional structures decreases and the time available increases, scenarios involving isolated observers gain relevance in discussions of long-term cosmic evolution. Boltzmann brains serve primarily as a thought experiment, illustrating the strange consequences that arise when thermodynamics and cosmology are considered over extreme durations. They demonstrate how statistical reasoning challenges intuitive assumptions about the origins of complexity. The concept does not assert that such observers currently exist or will exist, but emphasizes the peculiar outcomes of applying entropy-based models to the entire future of the universe. The idea underscores the interplay between order, probability, and time. In a universe governed by thermodynamic principles, high-entropy states dominate overwhelmingly, yet fleeting islands of order can still arise through chance alone. These rare states contribute to the theoretical landscape of cosmology, offering a way to explore the limits of statistical interpretation. The Boltzmann Brain scenario remains a conceptual tool rather than a definitive model of cosmic evolution. It reflects the complex relationship between disorder and structure and the unusual consequences that emerge when probability is extended across unbounded time. Within this framework, the universe becomes a place where even the most improbable arrangements can momentarily appear, shaped by the vast expanse of time and the steady progression of entropy. The dark forest theory. In this perspective, the universe is imagined as a vast and silent forest, where every civilization is like a lone wanderer moving carefully between the trees. Each one carries the deep awareness that others may exist, but none can be sure of their intentions. In such an environment, silence becomes the most natural strategy for survival. The theory suggests that the cosmic quiet we observe may not be a mystery at all, but a logical outcome of countless societies choosing to hide rather than risk drawing attention to themselves. The idea begins with the enormous scale of the cosmos. With billions of stars and planets spread across unimaginable distances, it seems almost certain that life could arise many times. Yet the night sky remains quiet. No signals, no signs, no evidence that another technological society has chosen to announce its presence. The theory responds to this silence by proposing that communication is inherently dangerous. If one society reveals itself, it cannot predict whether the observer will be peaceful, cautious, or aggressively expansionistic. Because of this uncertainty, many civilizations may simply avoid revealing any information about themselves. This caution becomes even more intense when considering the difference in technological levels between societies. In a universe filled with countless worlds, it is likely that some civilizations rise earlier, advance farther, and gain abilities that others cannot anticipate. A small technological gap may create a large difference in influence. And if a more advanced society believes that new arrivals might compete for resources, territory, or influence, it may choose preemptive action simply to secure its own stability. This chain of reasoning turns the cosmic forest into a place where movement is slow, speech is rare, and every presence is carefully concealed. In this environment, even passive detection becomes a risk. A civilization that broadcasts its location might be compared to someone lighting a fire in a dark forest, where any observer, visible or hidden, could notice. A distant, unknown society may not have the patience to evaluate intentions or wait for communication. Instead, it might act swiftly to avoid any long-term uncertainty. The silence we detect from Earth may be the natural result of this careful approach repeated across countless worlds. The theory also highlights how limited our understanding truly is. We observe only a thin portion of the electromagnetic spectrum, and even that is influenced by dust, gas, and cosmic structures. If civilizations hide carefully, using tightly focused communication or internal networks that never leak into open space, we would have no way to detect them. Their presence could be nearby or extremely distant, and still completely invisible. The absence of evidence becomes less of a puzzle and more of a predictable outcome in a cautious universe. At the same time, this perspective adds weight to the idea that our own broadcasts, probes, and attempts to reach out may carry unknown consequences. Technological societies grow, expand, and change, and as they do, their needs shift. In a cosmic forest, announcing one's presence may be seen as an unnecessary risk. For emerging civilizations, silence may be a natural instinct, born from the same reasoning that governs countless others distributed across the stars. Viewed as a whole, the dark forest theory paints a universe filled not with the absence of life, but with the presence of quiet and careful observers. Each one watches the sky with patience, listens without revealing itself, and calculates its steps with long-term caution. This scenario does not rely on hostility or conflict as general rules, but rather on the simple uncertainty that accompanies encounters between unknown societies. In such an environment, silence becomes both a shield and a strategy. This explanation turns the cosmic quiet into something deliberate and methodical. The stars remain mute not because nothing exists, but because everything listens. The Doomsday Argument. The Doomsday Argument is built on a simple yet unsettling line of reasoning. It begins with the idea that every person exists at a specific point in the long timeline of human history. If one accepts that position as random among all humans who will ever live, then the total number of future generations might be far smaller than many imagine. The argument does not rely on catastrophic events, conflicts, or cosmic phenomena. Instead, it uses probability to outline a scenario in which humanity is already living somewhere near the middle of its overall existence. According to this perspective, every human who has lived or will live can be placed in a long sequence. In this chain, each person occupies a numbered position, forming a vast continuum of past, present, and future individuals. If someone finds themselves relatively early in this sequence, it could imply that the total number of future individuals is extremely large. But if someone finds themselves closer to a central point, the total number of people yet to be born might be limited. The argument suggests that it is statistically unlikely for an individual to exist extremely early in the overall population count of a civilization destined to produce trillions upon trillions of future members. This reasoning draws on the idea that being born at any particular moment should be considered an ordinary placement rather than an exceptionally early one. If humanity were to continue for countless generations, expanding across planets and producing an enormous population, then people alive today would appear unusually early in the sequence. The Doomsday Argument proposes that such an early placement is improbable. Instead, it suggests that a more modest total number of future humans is consistent with where we find ourselves in the timeline. This does not announce any specific event or time limit. Rather, it implies a shortened continuation relative to extremely long or expansive projections. The argument also considers the nature of civilizations that grow in size. When a society expands rapidly, its population can increase at remarkable rates. In such situations, large portions of the total population may come from just a few generations of growth. Because of this, even slight adjustments in future population size can significantly shift the expected placement of individuals within the overall human sequence. This sensitivity reinforces the idea that our current moment may correspond to a point of moderate rather than extreme expansion. Another aspect of the argument involves the uncertainty surrounding future developments. Humanity may encounter challenges that naturally limit its long-term growth. These challenges need not be dramatic or destructive. They might arise from the difficulty of maintaining large populations indefinitely or from the limitations of environmental or technological systems. The Doomsday Argument does not attempt to predict the nature of these limitations. Instead, it treats them as general possibilities that shape how long a civilization can continue without producing numbers far beyond what we observe in the present. What makes this line of thought notable is its restraint. It offers no scenario, no mechanism, and no countdown. It does not require sudden events or unusual shifts. Instead, it relies solely on statistical reasoning and the ordinary placement of individuals within a sequence. The quiet weight of the argument comes from its simplicity. If one assumes a random position among all the humans who will ever exist, the likelihood of being among the earliest members of an enormous future population becomes small. In this sense, the Doomsday Argument outlines a perspective where humanity's timeline may be shorter and more compact than commonly imagined. It neither predicts nor prescribes. Instead, it presents a frame through which to view our position in history, suggesting that the total span of human existence may not stretch indefinitely far into the future. Quantum immortality. Quantum immortality is a perspective that emerges from a particular interpretation of quantum mechanics, one in which the universe is constantly branching into countless possibilities. In this framework, every event that can happen does happen, each one unfolding along its own path. Within this landscape of diverging outcomes, a unique idea takes shape: the notion that an individual consciousness might continue along the branches where it persists, creating an unbroken line of subjective experience that avoids its own disappearance. This perspective does not describe physical immortality in the traditional sense. Instead, it explores how experience might continue through the quantum structure of reality, following the paths in which survival remains possible. The idea begins with the concept of branching events. In the quantum view, particles and systems do not commit to a single outcome until observed. Instead, they spread across multiple potential states. When the universe chooses an outcome, what actually occurs in this interpretation is a branching of the world into parallel versions. Each branch contains one possible result, and every observer finds themselves in one of those branches. From this, the idea of quantum immortality suggests that an individual may always find themselves in the branch where they continue to exist. While many branches may come to an end for that individual, the experience would naturally follow the surviving paths, forming a continuous thread of awareness. This concept leads to a perspective where the boundary between existence and non-existence becomes less absolute. When faced with events that present many possible outcomes, some branches may end abruptly, while others unfold safely. In this interpretation, the individual's experience is always carried forward by the branches where continuity is maintained. The theory does not influence physical events or alter probabilities. Instead, it focuses on the internal viewpoint of consciousness, imagining it navigating through a vast sea of possible futures, always moving along the channels where it remains intact. Within this framework, time becomes a series of quiet transitions between branching possibilities. A person might encounter situations where outcomes vary widely, from minor changes to major divergences. In many branches, the path may end in a way that the individual cannot experience. Yet in other branches, the sequence continues without interruption. From the internal perspective, the journey feels smooth and unbroken. The quiet persistence of consciousness through these surviving paths is what shapes the idea of quantum immortality, presenting a vision of experience that stretches through the intricate architecture of quantum possibilities. An important aspect of this perspective is that it does not imply that a person avoids challenges, harm, or loss. Branches can still shift in countless directions, and the journey through the surviving paths may be marked by difficulties or unforeseen changes. Quantum immortality simply suggests that subjective experience remains tethered to continuity. While external observers may describe a situation using probabilities, the internal view follows the single thread that remains unbroken, even if it becomes increasingly narrow among the vast network of branching outcomes. Another dimension of the idea involves the nature of awareness itself. In this interpretation, consciousness is not treated as something that rises above physical processes, but rather as something that flows through them. Each moment of awareness is tied to a particular branch. As the universe divides into new possibilities, awareness follows one of the continuing paths. This perspective does not make claims about the origin of consciousness or its deeper structure. Instead, it focuses on the way awareness might interface with the branching fabric of quantum mechanics, resulting in a persistent line of experience. Over long stretches of time, this idea forms a view where an individual might perceive an unusually extended continuity. While countless branches may fade away, the path that remains becomes the one the person experiences. This does not guarantee comfort or stability. It simply outlines a scenario in which awareness consistently moves into the versions of reality where it endures. In this sense, quantum immortality presents a unique and contemplative perspective on the relationship between consciousness and the quantum world, suggesting that within the vast and branching expanse of possibilities, subjective experience might follow a single, continuous thread that never fully reaches an end from its own point of view. Rogue black holes. Rogue black holes are objects that drift through space without a host galaxy, star system, or stable orbit. They move silently across the cosmic landscape, shaped only by gravity and the momentum of past events. Unlike black holes formed at the centers of galaxies or within stellar clusters, these wanderers travel alone, without emitting light or radiation unless they encounter matter. Their presence is nearly impossible to detect directly, making them some of the most elusive objects in the universe. The idea of rogue black holes introduces a perspective in which powerful gravitational forces move quietly through space, hidden from observation until they interact with their surroundings. Their origins trace back to dynamic cosmic events. In some systems, interactions between multiple massive objects can create instabilities, sending one of them outward at high velocity. When this occurs with a black hole, the result is a solitary traveler pushed far from its birthplace. In other cases, the collapse of a massive star may produce an asymmetric release of energy. This uneven distribution can impart a strong momentum to the newly formed black hole, giving it a kick that propels it into interstellar space. Over time, these events accumulate across billions of years, producing a population of drifting compact objects that move independently through the galaxy. The motion of these wanderers is shaped entirely by gravitational influence. They may travel for millions of years without encountering any significant material. Interstellar space is vast and mostly empty, allowing a rogue black hole to pass unnoticed. Only when it interacts with gas, dust, or a star does its presence become detectable. The gravitational pull can distort or draw in surrounding material, forming a temporary disk of heated matter. This glowing structure makes the black hole visible to distant observers, but such events are rare. Most of the time, a rogue black hole remains cold, dark, and silent, slipping through the galaxy without leaving a trace. Despite their quiet nature, their influence extends far beyond direct encounters. As a rogue black hole passes through a region, it subtly disturbs the orbits of nearby stars and interstellar objects. In systems with complex gravitational balances, even slight perturbations can accumulate over long stretches of time. These small changes are not immediate or dramatic. They unfold slowly, creating gentle shifts in motion that build gradually. On cosmic timescales, these effects can alter the paths of stellar groups or reshape the distribution of interstellar material. The possibility of these wanderers passing near planetary systems adds another layer to their significance. A rogue black hole does not need to collide with a star or planet to leave an impact. Its gravitational field alone can stretch or redirect the orbits of celestial bodies. In some imagined scenarios, a passing black hole could influence the outer regions of a planetary system, drawing distant objects inward or outward. These changes might unfold gradually, leaving the inner system undisturbed while altering the structure of its outskirts. Such events remain extremely rare, yet they highlight the subtle power these objects hold as they move through the galaxy. An interesting aspect of these wanderers is their potential to gather material over long distances. When traveling through regions with slightly denser gas or clusters of dust, a rogue black hole may attract small amounts of matter. This material spirals inward slowly, producing faint emissions detectable only with sensitive instruments. These emissions can reveal the presence of an otherwise invisible object. Through observations like these, astronomers can study the motion, mass, and behavior of rogue black holes, building a clearer understanding of how they shape the galactic environment. The existence of rogue black holes also expands the perspective on how galaxies evolve. Over billions of years, stars form, collapse, collide, and disperse. Black holes created in these processes may be ejected or drift away from the structures that shaped them. This continuous redistribution of mass contributes to the subtle balance of gravitational forces across the galaxy. Rogue black holes become part of the long-term story of stellar evolution, carrying with them the history of the systems they once occupied. Viewed from a broader standpoint, rogue black holes represent the quiet and wandering side of cosmic evolution. They lack the dazzling displays associated with active galactic centers or bright stellar remnants. Instead, they embody a form of silent motion, shaped by gravity alone. Their presence suggests a universe filled with unseen travelers, each one moving through the dark spaces between stars, influencing their surroundings in slow and measured ways. Goo Scenario. The Goo Scenario is a perspective built around the idea of self-replicating microscopic machines, devices capable of copying themselves using available material from their environment. These machines, often imagined at the scale of molecules, represent a form of technology that could, in theory, duplicate with extraordinary speed. The scenario envisions a situation in which these replicators grow beyond their intended purpose, continuing to multiply without restraint. Over time, they could convert surrounding matter into new copies of themselves, creating an ever-expanding wave of replication that transforms everything it touches. The focus of this idea is not on a sudden or dramatic event, but on the quiet potential of exponential growth. The concept begins with the nature of replication. Even a single self-copying machine, if designed to reproduce efficiently, could produce a vast number of descendants in a relatively short period. 1 becomes 2, 2 become 4, and the sequence continues. At first, the change is subtle, almost invisible. Only after many cycles does the process accelerate into something noticeable. This pattern of growth is common in biological systems, but when applied to artificial devices capable of operating without the usual limitations of living organisms, the scale becomes much larger. The Goo Scenario explores what might occur if such replicators continued their activity without control, guidance, or natural boundaries. In this imagined situation, the machines do not require complex materials. They would extract basic elements from soil, rock, or organic matter, reorganizing them at a molecular level. The process would not be dramatic or explosive. Instead, it would unfold as a steady transformation of the environment. A patch of ground, a body of water, or even atmospheric particles could gradually become part of a growing mass of microscopic structures, each one continuing the cycle. Over long stretches of time, the accumulation becomes increasingly significant, creating vast quantities of identical units, an expanding field of tiny, active machines. The scenario also examines the challenge of containment. Self-replicating systems, once dispersed into the environment, can become difficult to monitor. Unlike large machines or complex technologies, microscopic replicators can spread through air, water, or soil. Their presence may not be immediately noticeable, especially if early replication takes place in regions that are rarely observed. By the time the effects become clear, the number of replicators may already be beyond straightforward control. This aspect of the idea highlights the importance of precision and stability in technologies designed to operate at extremely small scales. Another dimension of the scenario involves the energy sources these devices might use. If they rely on ambient heat, chemical reactions, or sunlight, they could function in a wide range of environments. This adaptability gives them the potential to expand gradually across diverse landscapes. Their growth pattern might vary depending on local conditions, slowing in some areas and accelerating in others. The cumulative effect, however, remains consistent. Each unit produces new units, and the total number increases steadily over time. From a broader perspective, the Goo Scenario reflects on the relationship between technological advancement and long-term stability. It emphasizes how powerful tools, if not carefully controlled, can produce outcomes that drift far from their original purpose. The scenario is not presented as an inevitable future, but as a reminder of how exponential processes can behave when interacting with the physical world. The quiet persistence of replication becomes the central theme, illustrating how small beginnings can lead to large-scale transformations. In its full scope, the Goo Scenario presents a vision of microscopic machines that operate with simple rules yet produce vast consequences. It is not centered on conflict or sudden change. Instead, it describes a gradual, unbroken expansion driven by the logic of replication. The image of a slowly growing mass of identical units, each one built from the materials around it, captures the essence of this perspective. It offers a contemplative view of how advanced technologies might behave if they move beyond containment, creating a world shaped not by intention, but by the quiet and continuous process of self-multiplication. The Planetary Brain. The planetary brain is a perspective that imagines an entire world gradually developing the characteristics of a unified, interconnected system of information. In this view, networks of communication, data, and sensing technologies begin to function together in a way that resembles a vast, distributed mind. It does not depend on a single structure or controlling center. Instead, it emerges from countless smaller components, devices, sensors, communication pathways, and storage systems, slowly forming a network that gathers, processes, and circulates information across the whole surface of a planet. The idea focuses on the long-term development of connectivity and how it might evolve into an integrated global system. The concept begins with the observation that technological societies tend to expand their networks over time. Simple communication channels grow into complex digital infrastructures. As these infrastructures deepen, they begin to link more aspects of daily life, from personal devices to environmental monitoring tools. Gradually, entire regions become covered by a web of data exchange. Each element contributes a small part, gathering information, responding to changes, or transmitting signals. Over many years, the accumulation of these connections forms a structure that is not centralized but still coordinated through the flow of information. This interconnected structure can be compared to a neural network, though the resemblance is metaphorical rather than biological. Individual devices act like nodes, transferring data between one another. Large systems such as weather satellites, transportation grids, and global communication networks serve as massive clusters of information exchange. Together, these elements create a dynamic field in which data moves continuously, shaping decisions, responses, and automated processes. In this sense, the planetary brain is not a conscious entity, but a pattern of widespread sensing and reaction distributed across a vast scale. One of the defining features of this idea is the way information becomes shared. Local events, changes in temperature, movement of objects, fluctuations in energy use, can be detected by sensors and transmitted across the network. Algorithms then analyze this information and adjust various systems accordingly. These responses may influence infrastructure, environmental regulation, traffic flow, or resource distribution. Over time, this cycle of sensing and adjustment creates a feedback loop that resembles the way biological systems respond to stimuli. The planetary brain emerges from these layered interactions rather than from a single source of control. Another aspect of this perspective concerns the growth of storage and processing capacity. As digital systems expand, the amount of information collected increases dramatically. Data centers, computational clouds, and decentralized storage systems form reservoirs where information can accumulate. These reservoirs support long-term analysis, pattern detection, and large-scale modeling. In this view, the planet becomes a place where memory is not held by individuals alone but preserved across a network that spans continents. The continuity of this memory contributes to the evolving structure of the planetary brain. The idea also highlights how communication networks extend beyond human interaction. Machines communicate with each other directly, exchanging data without the need for human intervention. This machine-to-machine communication forms a layer of activity that operates constantly in the background. It coordinates infrastructure, maintains systems, and updates information in real time. Because of this continuous flow, the network gains a form of persistence. It does not sleep or pause. It processes and adjusts without interruption, reinforcing the perception of an active planetary system. Over long periods, the cumulative effect of these systems shapes the environment itself. Energy grids adapt to patterns of demand, transportation networks synchronize their movements, and environmental sensors adjust regulatory systems automatically. The planet becomes a place where numerous processes are interconnected, guided by the constant exchange of data. This does not imply the presence of intention or awareness. Instead, it illustrates how complexity can arise naturally from the interaction of many smaller parts, forming a structure that behaves in a coordinated and responsive way. In its full expression, the planetary brain is a vision of a world where technology, communication, and data integrate into an enormous, distributed network. It is not a being and it does not possess thoughts. Rather, it is a metaphor for the scale and reach of interconnected systems that grow over time. As each part contributes to the flow of information, the planet begins to resemble a single, unified field of sensing and response, an intricate structure shaped by the continuous movement of data across its surface. False vacuum theory. False vacuum theory begins with the idea that the universe may not be in its most stable possible state. In this perspective, everything we observe, matter, energy, forces, and the structure of space itself, might rest on a foundation that is only temporarily stable. The vacuum, which appears empty, is viewed as a field with certain energy levels. If the current state of that field is not the absolute minimum, then it is considered a false vacuum. This means the universe could, in principle, transition to a more stable state, one with a lower energy configuration. Such a transition would not resemble natural change as we understand it. Instead, it would unfold through the fundamental fabric of space, a shift that redefines the basic rules governing reality. This idea arises from quantum field theory, where even empty space is not truly empty. It contains fluctuating fields with inherent energies. These fields can settle into various configurations, some stable and some only metastable. A metastable state can endure for an extremely long time, millions, billions, or even trillions of years, yet still not be the final, most stable configuration. False vacuum theory suggests that the current state of the universe is one of these long-lived but not ultimately stable phases. In this view, the vacuum persists quietly, holding the structures of the cosmos together while still harboring the potential for transition. The transition itself is imagined as a quantum event. In a rare and unpredictable moment, a small region of space could shift into a true vacuum state. This region, often described as a bubble, would carry different physical properties than the surrounding space. In the true vacuum, the values of fundamental fields could change, altering the forces that govern matter. Once formed, such a bubble would expand outward at extraordinary speed, not because of force or pressure, but because the true vacuum is more stable. The boundary between the two states would move outward, converting the false vacuum into the true one as it advances. One of the most striking aspects of this perspective is that the transition would not proceed slowly or gradually. Instead, the bubble would expand at a speed that approaches the universal limit set by physics, advancing across space with remarkable efficiency. Because it changes the structure of the vacuum itself, the boundary would reshape the properties of matter, energy, and physical constants within its path. At a fundamental level, the laws of physics inside the bubble could differ in ways that alter the behavior of particles and forces. Each region converted to the true vacuum would follow these new rules, forming a cosmos that is distinct from the one we know. The theory emphasizes that this process is entirely natural within the framework of quantum physics. If a vacuum state is not absolutely stable, it carries a finite chance of transitioning. This chance is extremely small, so the false vacuum may persist for extraordinary lengths of time. But even a very small possibility, when stretched across the immense age and volume of the universe, leaves open the potential for such a transformation. The uncertainty of when or where a transition might occur becomes part of the theory's quiet weight. It does not predict a timeline or a location. It merely outlines a possibility inherent in the structure of the vacuum itself. Another dimension of false vacuum theory lies in how subtly the universe could be balanced. The energy levels of fields might be positioned so delicately that even slight differences determine whether the vacuum is stable or metastable. These delicate balances shape the behavior of particles, the formation of atoms, and the evolution of stars. In this sense, the entire cosmic structure may rest on a finely tuned plateau, one that appears solid but could, in principle, give way to a deeper level. This does not imply fragility in the everyday sense. Instead, it reflects the profound sensitivity of the universe's underlying fields to their energy configurations. The theory also highlights the distinction between observation and underlying reality. Even if the universe appears stable, observations cannot always reveal the true nature of the vacuum. Experiments can probe only a portion of the energy landscape, leaving deeper levels unexplored. The boundaries of knowledge in this area are shaped by limitations in measurement and by the difficulty of recreating the conditions present during the earliest moments of the cosmos. As a result, the question of whether the vacuum is true or false remains open, suspended between theory and the limits of experimental insight. In its full scope, false vacuum theory presents a universe that appears calm on the surface yet may contain within its foundations the potential for profound transformation. It describes a reality built on fields that have settled into a long-lived but uncertain state, holding the structures of the cosmos together while also containing the possibility of deeper stability. The theory offers a contemplative view of existence, suggesting that the universe may rest in a delicate balance shaped by the energy of the vacuum itself. Quiet, enduring, and still not necessarily final. Time loop universe. The time loop universe is a perspective that imagines the entire cosmos following a repeating cycle, where the sequence of events eventually returns to its starting point. In this view, time does not stretch endlessly forward in a linear progression. Instead, it forms a closed structure, looping back on itself after an immense duration. The universe expands, evolves, transforms, and then, at the end of its vast cycle, returns to conditions nearly identical to those at its beginning. This repetition is not abrupt or mechanical. It unfolds gradually, shaped by the long-term behavior of matter, energy, and the geometry of space-time itself. The idea begins with the structure of time. In everyday experience, time appears to move forward in a straight line, carrying events from the past into the present and then into the future. But certain cosmological models suggest that under specific conditions, space-time could curve in such a way that the direction of time eventually loops around. This loop would be enormous, stretching across unimaginable lengths, with full cycles lasting far longer than the lifespan of stars or galaxies. Within such a framework, the entire history of the universe, its formation, its evolution, and its final transformation, would repeat endlessly, each cycle containing its own version of cosmic events. In a time loop universe, each cycle resembles the last, but not in a rigid or deterministic way. The conditions at the end of one cycle gradually merge into those at the beginning of the next. These conditions determine the formation of particles, the development of structures, and the emergence of cosmic patterns. Over long stretches of time, the universe would pass through familiar phases. Dense and hot in its earliest moments, expanded and structured in its middle, and then slowly shifting toward the conditions needed for the cycle to begin again. The return is subtle rather than abrupt, shaped by the geometry and energy of spacetime. An important aspect of this perspective involves the behavior of entropy, the measure of disorder. In a typical linear universe, entropy increases steadily, driving the cosmos toward a state of uniformity. But in a cyclical model, the end of the cycle must connect with the beginning. This means that conditions of increasing entropy eventually transition into a state where entropy resets. The details of how this reset occurs vary in different versions of the idea, but the central theme remains the same. The universe contains mechanisms that allow it to return to a low entropy state, restarting its progression through familiar phases. Within this framework, time does not end. Instead, it bends. A distant future is not an endpoint but a pathway back toward the past. This looping structure allows for a repetition of cosmic history without requiring perfect duplication of every detail. Small variations may arise in each cycle, shaped by the complex interactions that unfold over billions of years. Yet the overall rhythm remains recognizable. Galaxies form, stars ignite, worlds develop, and the universe eventually prepares for renewal. Each cycle becomes part of a larger pattern, repeating endlessly across the structure of time. From a broader perspective, the time loop universe highlights the possibility that cosmic history may be far deeper than a single timeline. If cycles repeat indefinitely, the universe may have existed through countless prior iterations, each one contributing to the long arc of cosmic evolution. The idea does not imply awareness or memory across cycles. Instead, it illustrates how the geometry of spacetime can shape the large-scale behavior of the cosmos, producing a repeating sequence of events that stretches far beyond human scale. Another dimension of this perspective involves the nature of beginnings. In a linear universe, the beginning is a singular event. But in a looped structure, the beginning becomes inseparable from the end. The early moments of the cosmos are linked to its far future, forming a closed circle rather than a trajectory with a boundary. This connection suggests that the universe is self-contained, with each cycle serving both as a conclusion and a renewal. The flow of time becomes a continuous path with no ultimate origin point. In its full expression, the time loop universe presents a reality in which the cosmos is shaped by repetition on the grandest scale. It offers a view of time that extends beyond linear progression, imagining a structure where the universe evolves, loops, and begins again. This perspective describes a cosmos that moves through phases of growth and transformation, returning eventually to its earliest conditions and continuing the cycle indefinitely. It is a contemplative vision of time as a vast circular path, guiding the universe through endless cycles of existence. The Kardashev Collapse. The idea behind the Kardashev Collapse begins with a simple scale designed to measure the technological reach of civilizations. This scale, created by astrophysicist Nikolai Kardashev, assigns levels based on how much energy a civilization can harness. A Type 1 civilization commands all energy available on its planet, a Type 2 accesses the full output of its star, and a Type 3 controls energy on the scale of an entire galaxy. It appears to be a roadmap for progress, a ladder that any ambitious species might try to climb. Yet embedded in this framework is a quiet tension, the assumption that growth can continue indefinitely. The concept of the Kardashev collapse challenges this optimism by suggesting that the climb might not only be difficult but fundamentally unsustainable. The theory proposes that civilizations tend to fail long before reaching even the first step on this scale. Rather than advancing smoothly toward planetary mastery, they encounter diminishing returns. The costs of expanding energy infrastructure grow faster than the benefits. Complex technologies require equally complex systems to maintain, repair, and regulate. As these systems multiply, they begin to strain the foundations of the civilization that created them. Energy demands rise, but efficiency fails to keep pace. Maintenance becomes more difficult. Fragile, interconnected networks start to buckle under their own weight. And in this growing imbalance, collapse becomes not an exception but an expectation. Underlying this idea is the notion that exponential growth, often imagined as a hallmark of progress, eventually confronts limits that cannot be avoided. A civilization striving toward Type 1 status must expand its energy capture far beyond modern levels. Yet every step toward this goal introduces new layers of complexity. Energy grids, resource extraction systems, data networks, environmental protections, and social stability all need to evolve in coordination. If any one of these components falls out of alignment, the resulting pressure can ripple outward until the entire system destabilizes. The collapse may not happen suddenly. It can unfold slowly, a subtle eroding of capability until the civilization no longer maintains the momentum it once had. This framework suggests that the universe might be filled with societies that attempted to grow but reached a threshold where continued expansion became impossible. They may have operated under the assumption that every problem could be solved with more energy and more advancement, only to discover that their own infrastructure had become too large to manage. In this view, the absence of visible megastructures in space is not surprising. The step from a Type 1 to a Type 2 society requires such extraordinary coordination that most civilizations never come close. Instead, they remain confined to their planetary limits until internal pressures redirect them away from massive energy projects or cause their decline. The Kardashev collapse does not necessarily describe a catastrophic ending. Instead, it can manifest as a plateau in development. A civilization may simply stop advancing, redirecting its focus from expansion to survival. It might preserve what it has rather than pursuing higher levels of the scale. Over time, its achievements could fade or fragment until only remnants remain. Alternatively, a civilization might gradually simplify itself, reducing its energy consumption to prevent instability. In either case, the trajectory moves downward or stagnates instead of upward. The scale, designed to measure success, becomes a mirror of limitation. Some interpretations of this idea consider the biological and social constraints entwined with technological advancement. As systems become more complex, they depend increasingly on stability of environment, resources, knowledge, and governance. Yet stability is fragile. Natural disruptions, internal tensions, or subtle shifts in planetary conditions can stress the network. If the civilization cannot adapt at a pace equal to the pressures acting upon it, the imbalance accumulates. Once that imbalance grows too great, collapse becomes not just possible but difficult to avoid. A society may understand its predicament, yet the speed of change may outstrip its ability to respond. This theory adds a quiet layer to the broader discussion about cosmic silence. If many civilizations encounter similar obstacles, the universe may contain countless worlds caught in a loop of attempted progress followed by contraction. They never reach the visibility required for detection because they stall before achieving massive energy structures. They may endure for long periods, but always within local limits. Their histories rise and fall on a scale too small to be noticed from afar. The Kardashev Collapse is unsettling because it reframes progress as something that may not scale forever. It suggests that complexity carries hidden thresholds, and beyond those thresholds the structure becomes unstable. It presents a universe where advancement is not only challenging but inherently dangerous if pushed too far. Yet it also offers a kind of quiet realism, that survival might depend less on reaching higher levels of power and more on recognizing the boundaries that cannot be exceeded. In this view, the collapse is not a failure but a natural course. Civilizations grow, they explore, they innovate, and they reach for the limits of what is possible. But the universe sets its own conditions, and sometimes the most sustainable path lies not in surpassing those limits, but in understanding them. Alien Zoo Hypothesis. The Alien Zoo hypothesis suggests a universe where advanced civilizations observe emerging worlds without interference, allowing life to develop naturally while remaining under quiet supervision. It imagines a scenario in which humanity is not alone, yet remains isolated by design. In this view, Earth is part of a vast, carefully maintained reserve, a place watched from a distance, studied like a protected ecosystem, but never contacted directly. This hypothesis stands on the idea that if intelligent civilizations exist elsewhere, some may have reached levels of development far beyond anything humanity has achieved. With such advancement might come caution, restraint, and a responsibility not to disturb evolving societies until they reach a certain point of maturity. At the core of this idea is the belief that contact between civilizations at vastly different stages can be destabilizing. A highly developed society may possess technologies and perspectives that could overwhelm a younger species, altering its natural trajectory. Instead of sharing knowledge or revealing their presence, these advanced observers might choose a passive role, stepping back to minimize their influence. Earth would continue on its path, unaware of the forces ensuring that its development remains uninterrupted. In this scenario, the silence humanity experiences is not a sign of emptiness, but a deliberate choice made by those who watch from afar. The hypothesis draws from the concept of conservation, protecting an environment by avoiding direct interference. Just as humans create protected zones for wildlife, alien civilizations might apply similar principles on a cosmic scale. A developing world becomes a place of interest, not as a resource to be used, but as a natural system worthy of study. Observers gather data discreetly, perhaps using methods far beyond human detection. They would need no visible spacecraft, no signals, no physical presence. Their monitoring could be subtle, woven into the background of the universe in ways indistinguishable from natural phenomena. One of the more unsettling aspects of this theory is the implication that humanity's actions are being watched, catalogued, and analyzed. The decisions made by societies, the progress of technology, and the unfolding of history could all be part of a long-term observational study. Yet the watchers would not intervene, even in moments when their presence might seem justified. Their commitment to non-interference would hold firm, grounded in principles or policies developed long before humanity appeared. This creates a portrait of a universe where advanced civilizations act not as conquerors, but as custodians, following rules designed to safeguard emerging life. The alien zoo hypothesis also suggests that the apparent absence of extraterrestrial contact does not reflect a lack of interest. Instead, the silence becomes intentional. Communication is withheld, not because there is nothing to say, but because any message could alter the course of development. Observers wait until a species reaches a threshold, perhaps technological maturity, social stability, or the ability to understand and handle contact responsibly. Only then might the isolation end, if at all. Until that moment, the watched remains unaware, continuing to evolve within parameters designed to preserve its autonomy. In considering this idea, the role of advanced civilizations becomes one of careful restraint. They would need to maintain strict rules across vast distances and enormous timescales. Such discipline implies not only intelligence, but a stable and enduring system capable of coordinating many different actors. Their cooperation would ensure that no single group disrupts the experiment. This adds a layer of complexity to the hypothesis, suggesting an interstellar culture where observation is not merely a choice but a guiding principle. The alien zoo hypothesis challenges assumptions about exploration and communication. Instead of expecting a universe filled with visible activity, it imagines a quieter kind of presence, one that prioritizes stability and respect over interaction. For humanity, this perspective reframes cosmic solitude. The silence becomes meaningful, a sign not of abandonment but of careful distance. It suggests that the first contact expected by many might not come through signals or visits, but through the realization that the quiet has been maintained deliberately. This theory is intriguing because it redefines the boundaries between presence and absence. Even if watchers exist, they remain hidden by intention, creating a situation where humanity's understanding of its place in the universe is shaped by something it cannot detect. The idea offers a gentle tension, the possibility that the universe is neither empty nor hostile, but observant and patient. In this reserved quietness lies a sense of mystery, suggesting that the story of contact may unfold not through sudden discovery, but through gradual recognition that silence itself can carry meaning. Ending. As we reach the end of this journey through the theories that unsettle even the brightest minds, take a moment to let the ideas settle. If this exploration gave you something to think about, consider supporting the channel. Leave a like, subscribe, and share your thoughts in the comments. Your perspective adds depth to these discussions. And if you know someone who would enjoy reflecting on these mysteries, share the video with them. Each conversation helps this space grow, and together we continue exploring the unknown.